Hello, we'll start with revision problems on chapter 6. So we want to calculate first the power in a wind moving with a speed u equals to 5 meters per second, incident on a wind turbine with blades of 100 meter in diameter. How does the power change if the wind speed increases to u equals to 10 meter per second? Assuming that density of air is equal to 1.2 kilogram per meter cube. So first, we should know what are the different parameters affecting the power. We know that if we have a certain cross-section of the wind turbine, and this cross-sectional area is exposed to the wind in a perpendicular direction with a velocity u, we know that the power that can be extracted is equal to half times A times rho times u to the power 3. هذا we should know it. When we derived the formulas wind energy, okay, we learned that how we can determine the value of power at a certain section. So we should know these relations and how to work with them, okay? So here, we have the cross-sectional area A, we have the velocity u, okay, and we have u cube. If you forgot, you can reconstruct the formula because you know what is the mass flow rate m dot. The mass flow rate is equal to rho times area times velocity, okay? And A times V is the volumetric flow rate Q. So Q is in meter cube per second. And m dot is in kilogram per second, okay? No, it's fine, no problem. Okay. Yes, I know, but no, it's easier for me. Okay? So, we know that if I consider, okay, the value of energy per unit volume. What is the value of energy per unit volume? It's half rho u square. Wind energy, yes. Okay, so if you do half rho u square, this will give you energy per unit volume. So it's joule per meter cube. So if you want to get the power, I should multiply the energy per unit volume, which is half rho u square, by what? By the volumetric flow rate, Q. Because when you do times meter cube per second, what will be the unit? Watt. Okay? So if you forgot the formula, you can reconstitute this formula because you have that the energy per unit volume is half rho u square. And when I multiply it by Q, which is the volumetric flow rate, I get the power. That's why the power is half A rho u to the power 3. So it's proportional to u cube. Okay? Now, we have all parameters needed. We know the velocity of wind. We know the diameter. So we just have to calculate the cross-sectional area, which is pi d square over 4 or pi r square, okay? And then we get, in order to get the power in watt, units should be meter square for the area, kilogram per meter cube for the density, and meter per second for the velocity, okay? And then you get the value in watt, but since you have a big number, you divide by 10 to the power 6. And if you multiply by 10 minus 6, you will get the value in megawatts, okay? Now, what will be, without doing any calculation, okay, if they tell us the power, what will be the value of power if the wind speed is equal to 10? So we multiplied u by 2. So since from our expression, the power is proportional to u to the power 3, okay? So if we multiply velocity by 2, the power will be multiplied by 2 cube by 8. So we can just do 0.6 times 8. So we can say that if we double the velocity, the power will be much larger. It will be multiplied by 8 So it will be equal to 4.8 megawatt. That's why it's very important to select an appropriate location for our wind farms, because the velocity of wind will largely affect the power extract. Okay. Another problem. We want to calculate the average power output of a wind turbine with blades of 85 diameter operating in wind with a mean speed of 7 meters per second. At this wind speed, the power coefficient is 0.45. What do we mean by power coefficient? It's the coefficient of performance. So if you remember, we said that the coefficient of performance by definition is like it's an efficiency for our turbine. It's equal to the power extracted over the maximum possible power that can be extracted if we have a velocity u0 passing by the cross-sectional area. We know already that the maximum power that can be extracted is half times rho times u0 cube times the area of the turbine. But if you remember, we said that it's impossible to extract it completely because some part of the kinetic energy will remain because wind will be blown downstream of the turbine. So we cannot take the whole kinetic energy of wind. Okay, that's why we have this maximum will never be reached. Okay, and we have derived together, and you are responsible of the derivation of Betz limit. You need to know how I can find the maximum possible extracted fraction. Okay, which is around 59%. We'll see it together again. Okay, so in this problem, we have the area because the diameter is given. We know the upstream speed, u0. u0 represents the upstream speed, not the speed at the cross-section. The speed at the cross-section is u1, okay? And we have the density, and they told us that the power extracted, for the first part, we don't know the value of power extracted. We know the coefficient of performance. So here, what is our only unknown in first question? The only unknown in first question is the power. So we can just say that to calculate the power, we multiply the coefficient of performance, which is 45%, as expected, always smaller than 59%, which is the Betz limit. Okay, times half rho u0 cube times A1, and A1 is pi d square over 4. Now, we should know that for each turbine, okay, the coefficient of performance is largely dependent on the velocity of wind. So your coefficient of performance will vary with velocity, and we need to optimize the design depending on the location. If you have a location where in majority of time you have this speed, you should design your turbine in a way to have a maximum performance in this range of speed. That's why we should study the climate, how the velocity of wind is varying, in order to determine, depending on the location we select, what is the best design to use. Okay, so here, for example, they are telling us that if we have different conditions, and if we don't have a speed of 7 meters per second, if we work at 13 meters per second, the rated output power is 1.5 megawatt. So the power will increase, okay? Of course, this is expected because as the velocity will increase, the power will increase. But because the coefficient of performance is not the same, okay, we'll have, if you want, a new coefficient of performance to calculate. So to find what is CP at this velocity, we just have to apply now the formula as it is, because now we know the power, and we want to we know u0 and a1, and we want to calculate the value of the coefficient of performance. So for these conditions given, as expected, the power is much larger, but the coefficient of performance is lower. This means that this design is better, will work in a better performance at lower velocities. So with increasing velocities, the coefficient of performance was reduced. That's why we need to study, if you want, whenever we want to select an appropriate turbine, we should know how the coefficient of performance can vary with wind speeds. And depending on the locations that we have and the mean velocity of wind in such region, we can decide which design to use. So in these two first problems, it was just to understand the relations and to know how to apply them. But we can also have derivations, okay? That's why you should understand how we get the Betz limit. And sometimes, like in this problem, we can have a problem where we need to do some derivations in order to determine the coefficient of performance. Who is the coefficient of performance it's normalized already. It's a ratio. No, there is no formula. I will. But look, in these chapters, you don't have a lot of formulas. I will give you, like last time, I will list for you what you should memorize. Okay? And anything else will be provided. But you don't have a lot of formulas like in previous chapters. Okay? Okay. So, good luck. Okay. So, in this problem, consider two consecutive turbines exposed to wind with an upstream velocity u0. Until now, we studied for one turbine's performance, but in general, we have wind farms. We have a lot of turbines. Okay, so one turbine will affect other turbines. Why? Because consider you have two consecutive turbines. You have the first turbine here, and you have another turbine here. Okay, so actually, if I tell you that the upstream velocity of wind is u0, this is the upstream velocity of turbine number 1. Okay, but since turbine 2 is placed directly after turbine 1, so what will be the upstream velocity for turbine 2? u2. Okay, so this is the downstream velocity of turbine 1 and will constitute upstream velocity of turbine 2. Upstream before, downstream after. Yes. Okay. We want to consider two consecutive turbines exposed to wind with an upstream velocity u0, assuming that the second turbine extracts the maximum possible power. Calculate the maximum coefficient of performance of the system. So here we have two turbines. It's a system, and we need to calculate the overall coefficient of performance. Okay? So how to proceed? Let us move step by step. Okay? So first, to start with, we start with the same procedure for one turbine. You remember? What was the first formula we applied? Yes, we applied the momentum equation on the control volume of a turbine. Okay? From this equation, we said that we can find the force acting on the turbine. This force is simply equal to m dot times V upstream minus V downstream. Okay? And the mass flow rate m dot can be calculated at several sections. And it can be written as rho A0 U0, or if we consider the cross section of the turbine, it is equal to rho A1 U1. Okay, so that's why I replaced here m dot by rho U1 A1, and the upstream velocity is U0, and downstream velocity is U2. Okay? Atul al-force, yes. This is the force acting on the turbine. It's mass flow rate m dot. And just you say, applying the momentum equation, we get the force. And we know what is the power? Power is force times velocity. And since the velocity crossing this area is U1, so the power is obtained by doing force times U1. And no, U1 is not U0 minus U2. U0 minus U2, we did it because you need to consider U velocity upstream minus velocity downstream, because this is your control volume. Whenever you take a certain control volume and you need to find the force when you take air as control volume, you get the force of turbine on air. By action reaction, the force of air on turbine is the opposite. So if you take air as system, you do m dot V out minus V in. By action reaction, the force on turbine will be m dot V in minus V out. Okay? So you just have to know that this is the formula that will give you phi1 because m dot. How you calculate the mass flow rate? You know the area here. This is the area that you know. You know the cross-sectional area of your turbine. Yes, that's what. Okay? And you will relate, if you want, you will relate U2 to U1 by saying that I can calculate the power by two methods. The first method is by saying that power is force times velocity. And second method is to say that power is what? Is the variation in the rate of energy, the rate of kinetic energy. So what is the rate of kinetic energy at inlet? It's half m dot times U0 square, okay? And at the outlet, what is the rate of kinetic energy? So minus half m dot times U2 square, exactly. And since m dot is constant, because of continuity of the flow, m dot 0 equal m dot 1 equal m dot 2. So I can replace m dot by rho U1, A1. And now if I equate the two expressions of power, I can relate the U2 to U1 and U0. Because when you put these two expressions equal to each other, you can say that you can factorize this term. This is U0 minus U2 times U0 plus U2. Okay? And then when you do the simplification, because you have m dot in both expressions, when you use simplifications, you get that U2 is 2U1 minus U0. So now we can replace U2 in our expressions by 2U1 minus U0. Okay? If we replace U2 by its expression in the power, we get, this is the expression of power extracted by turbine number 1. Okay? And since we want to optimize power, we can define a coefficient A, okay? As we said, what will happen to the velocity as I move through my turbine? The velocity will decrease. That's why I can define a coefficient A between 0 and 1. And I will say that U1 can be written as 1 minus A times U0, okay? While for the second turbine, what is the upstream velocity? As we said, U2. Yani for turbine 1, we consider the upstream velocity U0. For turbine number 2, we consider the upstream velocity is U2. Okay? ليش في 2 turbines؟ لأنه in the problem we studied in the course material 1 turbine. Now they said if we put 2 turbines, 2 consecutive turbines, what will be the overall performance of the system? Exactly. And that's why I told you here, this is the second turbine. Okay, when you use your formulas, instead of U0 that you used for turbine number 1, you use U2 for turbine number 2. What is exiting turbine 1 will enter turbine, will be the upstream velocity of turbine 2. Okay? بس هي على الكروس section turbine 2 بيكون فيه 3. But what did they said that turbine 2 is extracting maximum possible power. And we know what is the expression of P max for a certain turbine. P max, okay, is half times rho times the cross-sectional area of the turbine times upstream velocity of this turbine, U upstream, cube. But what do we multiply by? CP, very good. The coefficient of performance. And نعم لا ما انت عندك P max هو CP بيكون CP maximum. اللي هي 0.59. It can be lower if you don't have maximum extraction. Okay, so this is the maximum possible power that I can extract. No, look, the actual power. What is the actual power extracted? It's half rho A times, what is the velocity crossing the section? U1. So if you want the actual value, it's half rho A U1 cube. Okay? What is the definition of CP? Definition of CP is this power over P max equal to, this is P max extracted. Yani I will write here extract. Okay? This is the maximum possible that you can extract. Because what is the actual? This is P actual. Okay? What is P actual by definition? P actual by definition equals to CP times half rho times area times U upstream cube. Okay? If you want to maximize the extracted power, the actual power, CP should be maximum. Exactly. So what is P maximum extracted? Yani the actual maximum. What is the actual maximum extracted? It's half rho A U upstream cube times the Betz limit, because if I want to extract maximum, if I want Q actual to be maximum, I need to maximize the coefficient of performance. Okay? So now I can say the following. I can say for turbine 1, they didn't say that turbine 1 is operating at maximum coefficient of performance. Okay? That's why I will define factor A. And I will say the power extracted by first turbine, as we derived together, is equal to 2 rho U1 square A1 times U0 minus U1. This is وين راحت السي بي؟ السي بي هون look, this is the actual power. هيدي الباور الاكشوال. انت متى بتحط سي بي this is equal to
سي بي times U1.
يعني if you do half rho A U0 cube, okay, you multiply by CP. But if you put U1 cube, you don't multiply by CP. And here, when we did the derivation together, we proved that the power can be written in 2 ways. Okay, you can use any of the 2 forms. Here, it's here. Okay, when you write the power, the first form is rho U1 A1 times U0 minus U2. Second form is P equal delta kinetic energy. So you can say that I can consider what, when I equate them. Yes. CP when you consider it relative to the maximum.
Okay, بس ما بدنا نستعمل CP أي velocity نستعمل.
When you want U1, لا, you use U1. If you want to get the value of the power at the cross section, okay?
نستعمل velocity
اللي عليها.
Okay, إذا نستعمل اللي قبلها نستعمل CP.
Yes, exactly.
ما في شيء خاص بالبعض. ما في شيء.
No. بس خاصة بالبعض المومنتوم. The momentum value. Okay. Look, there is, look here to understand it better. Okay. Here, whenever you know the velocity at this section, if you know it, here you know this velocity. And the problem that we are doing now, you don't know what is U1.
But U1 can be approximated to the average between the average phase and the problem.
No, it's not equal to the average. You can say, you can relate them. You related them through the following relation. يعني when you considered power equal power, بتطلع equal to the average, but we proved this. Because if you take U0 to the other side, you get that we have U1 equal U2 plus U0 over 2. It's right. You take the average, yes. It's right, and you can prove it through the following relation. You can do it, but if they tell you derive the Betz limit, you need to know how to do it. Okay, but it's right, because when we did the derivation, it is equal to if you want the average between the two. Okay.
This is only for the derivation.
Yes, this is for the derivation. Yes. In case they didn't ask you to derive, you have the right to use direct. Yes, but if they said derive the Betz limit, you need to go through the procedure. Okay. Yes, of course. معقول لا مش صعب الفحص. Okay. Yes. Okay. Yeah. Okay. So now, so this is the expression, okay, as we said, of the power extracted by first turbine. Okay, and we said that U1 can be replaced by 1 minus A times U0. Okay. So depending on the value, the value of A will change depending on the coefficient of performance of the turbine. Okay. So if I consider now, this is the power extracted by P1. Now for turbine 2, we said that turbine 2 is performing the maximum performance. So whenever you have maximum performance, we said that we can say that what is the coefficient of performance CP? It's equal to the Betz limit. And the Betz limit was proved in the course material to be equal to 16 over 27. That's why you can say that P2 is equal to half rho A U2 cube. Why we did U2? And what is the upstream velocity of turbine 2? It's U2. So that's why we did half rho A U2 cube times CP maxima. Okay. And we have that the value of P2, if we replace U2 by its expression, what was the expression of U2? As we said, we proved together that U2 can be expressed function of U1 and U0 equal to 2U1 minus U0. Okay, so if I replace U2 by its expression, I get what is the value of P2. So P2 extracted by second turbine is half rho A U0 cube times 1 minus 2A cube times 16 over 20. Okay, and now once we get this expression, we can calculate the total power. If we have two turbines, we should add their power. So the total power extracted, if we add the two expressions P1 plus P2, is equal to half rho A U0 cube times an expression function of A. And we said that we can, depending on the design, okay, we can vary A to see what is the optimal operation. Okay, so we now. Okay, what is A? A is the relation between the velocities upstream with velocity crossing a turbine. Okay, so this is U0, this is U1. We said that depending on the design of our blades, okay, the relation between U1 and U0 can vary, but always U1 will be smaller than U0. Okay, that's why we defined a coefficient A in a way that U1 is equal exactly to U0 times 1 minus A. And we need to optimize the design in a way to get A to give maximum performance. Exactly. So if you add the two expressions, you will get the power function of A. And then to find what is the optimal value of A to maximize the power, what do? We derive. So if we derive derivative of P with respect to A will give us the following expression. 5A minus 1 times A plus 1 equals to 0. So this derivative will be equal to 0. Of course, A equal minus 1 is rejected. Why? Because A is between 0 and 1. And if you consider this term, A is equal to 1/5. So therefore, we can say that for A equal 5, we can maximize the power. Okay, so we will try to do the design in a way to have A equals to 1/5. Okay, and then if you look at this expression, whenever you have the combination of the two turbines, what is the coefficient of performance? Where the coefficient multiplying half rho AU0 cube. What is CP? 16 over. Of course, it will be larger than the coefficient for one turbine because we added to the power of the two turbines. Okay. Any question on this?
So
Yes.
I need derivation resistor.
Yes.